Let us do some additional flange and web checks. Webs and flanges need to be checked, especially when a beam is subjected to concentrated loads. When steel members have concentrated loads applied perpendicular to flanges and symmetric to the web, their flanges and webs must have sufficient design strength against local flange bending, local web yielding, web crippling, and sideway web buckling. Chapter J of AISC specification on page 16.1-142 gives different checks for flanges and webs of steel members. The first check is the flange local bending. The flange of a steel member must be sufficiently rigid so that it will not deform and cause a zone of high stress concentration in the weld line with the web. The nominal tensile load that may be applied through a plate welded to the flange of a W section is to be determined by the expression given in J10-1. According to this expression, Rn is equal to 6.25 times the yield strength of the flange times thickness of the flange. The yield strength is in KSI, whereas the thickness is in inches. According to this specification, if the length of the loading across the member flange is less than 0.15 times the width of the flange, then equation J10-1 need not be checked. Please note that the expression J10-1 ensures that the flange doesn't bend in the weld line with the web. After this, there is another expression related to web local yielding. The local web yielding applies to all the concentrated forces, tensile or compressive. The local web yielding is shown in this figure. The nominal strength of the web of a beam at the web toe of the fillet when a concentrated load or reaction is applied is to be determined by one of the expressions given in the AISC manual. These expressions are J10-2 and J10-3. In these expressions, FYW is the yield strength of web in KSI, TW is the thickness of the web, K is the distance from the outer edge of the flange to the web toe of the fillet, and LB is the length of bearing in inches. Thus, FYW times TW small bracket 5 times K plus LB small bracket close will give us the expression J10-2. The expression J10-3 is FYW times TW small bracket 2.5K plus LB small bracket close. J10-2 is applicable where the concentrated load or reaction that causes tension or compression is applied at a distance greater than the depth d from the end of the member. So, in other words, if the concentrated load is applied at a distance d greater from the end of the member, then we use expression J10-2. Whereas if the force is applied at a distance d less from the member end, then we can use expression J10-3. In the case of unstiffened webs, we can have the so-called web crippling. Web crippling can be overcome by a stiffener or a doubler plate provided for at least half of the web depth. AIC specification gives three expressions for the web crippling: the expression J10-4, the expression J10-5A, and expression J10-5B. If the concentrated load is applied at a distance greater than or equal to d by 2 from the end of the member, where d is the overall depth of the member, then we can use the expression J10-4. In the expression J10-4 is 0.8 times the thickness of web square, big bracket 1 plus 3 times the bearing length by the overall depth times the thickness of web by thickness of flange raised to the power 1.5, big bracket close, times modulus of elasticity of steel into the yield strength of the web times thickness of the flange by thickness of the web times QF, where QF is equal to 1 for wide flange section and for hollow square sections in tension.
In the case of web crippling, when the concentrated compressive force is applied at a distance from the member end that is less than d by 2, then we can use the expressions in J10-5A and J10-5B. So in this figure, as we can see, the concentrated load is very close to the end. So in such cases, we can use the expression J10-5A and J10-5B. Now these two expressions depend on the ratio of the bearing length and the overall depth of the member. If the bearing length and overall depth ratio is less than zero point 0.2, then Rn will be equal to 0.40 Tw square, big bracket 1 plus 3 bearing length by depth ratio times the thickness of the web by thickness of the flange raised to the power 1.5, big bracket close, times modulus of elasticity into yield strength of the web times thickness of the flange divided by thickness of the web, square root times the constant QF. If the ratio of the bearing length and depth is greater than zero point 0.2, then Rn will be equal to zero point 0.4 times thickness of the web square, big bracket 1 plus small bracket 4 times the bearing length by depth minus zero point 0.2 small bracket close times the ratio of thickness of the web by thickness of the flange raised to the power 1.5, big bracket close, times the square root of modulus of elasticity, yield strength of the web, thickness of the flange by thickness of the web, times the factor QF. The fourth check is the web sideway buckling. In the case of web sideway buckling, the top flange is restrained, whereas the bottom flange is free to move. As a result of a concentrated load, the bottom flange has a tendency to rotate. So the code provides some conditions which, if satisfied, will ensure that the lower part of the flange won't buckle sideway. So if the compression flange is restrained against rotation, then we will have to satisfy the expression J10-6. For this expression J10-6 to be applicable, the ratio of web depth by thickness of the web divided by the ratio of the laterally unbraced length by width of the flange should be less than or equal to 2.3. Then we can take the nominal strength equal to CR times the thickness of the web cube times the thickness of the flange divided by the web depth whole square times big bracket 1 plus zero point 0.4 small bracket open the ratio of the web depth by thickness of the web to divided by the unbraced length ratio by the width of the flange. Small bracket close raised to the power 3 and then big bracket close. When the ratio of the web depth by thickness of the web to unbraced length by flange width is greater than 2.3, the limit state of web sideway buckling does not apply. The code also states that if the required strength of the web exceeds the available strength, local lateral bracing should be provided at the tension flange or either a pair of transverse stiffeners or doubler plate shall be provided. So in this figure, we have provided lateral bracing in order to avoid the sideway buckling. We can also provide a doubler plate as shown over here. So this blue doubler plate has been welded onto the I-beam in order to give more strength to its web. Similarly, we can have a stiffener welded to an I-beam and that also stiffens up the web. The code says that if the compression flange is not restrained against rotation and the ratio of the web depth by thickness of web to the unrestrained buckling length by the width of the flange is less than or equal to 1.7, then we can use the expression J10-7. According to this expression, the nominal strength Rn is equal to Cr constant times thickness of web cube times thickness of flange by the depth of the web square times big bracket zero point 0.4 times small bracket ratio of web depth by thickness of web divided by the buckling length by width of the flange whole cube and big bracket close. However, if the ratio of web depth by thickness of web to the unrestrained buckling length by width of the flange is greater than 1.7, then the limit state of the web sideway buckling does not apply. The constant CR used in the expression J10.6, J10, and J10.7 is equal to 960,000 ksi when the required flexure strength is less than the yield moment. This yield moment is corresponding to the yielding of tension flange and first yield of the compression flange. Similarly, CR is equal to 480,000 ksi when the flexure strength is greater than the yield moment. The specification also suggests that we should provide local lateral bracing at both the top and the bottom flange when the required strength of the web exceeds the available strength. The other check is web compression buckling. According to this check, the web compression buckling should be determined from expression J10.8 is equal to 24 times thickness of web cube times square root of modulus of elasticity times the yield strength of the web divided by the depth of the web times the factor QF. QF again is equal to 1 for wide flange section and for the hollow square section in tension. The specification says that when the pair of concentrated compressive force is applied at a distance from the end that is less than d by 2, where d is the overall depth, then the available strength shall be reduced by 50%. Again, in order to overcome the web compression buckling, we can provide a single stiffener or a doubler plate that is extending the full depth of the web. In case of beams, we can have the so-called unsymmetrical bending. Unsymmetrical bending typically occurs when the load applied to the beam is not symmetrically distributed with respect to the neutral axis of beam cross section. We know from our previous discussion that the beam cross section has a pair of mutually perpendicular axes which are known as principal axes, for which the product of inertia is zero. The bending that occurs about any axis other than one of the principal axes is actually called as the unsymmetrical bending. This happens when the external loads are not in plane with either of the principal axes, or when the loads are applied simultaneously to the beam from two or more directions. Unsymmetrical bending is easy to handle in the common shapes of steel beams such as W, S, M, or C sections. However, in the case of angle or Z sections, it is a bit challenging. In the case of unsymmetrical bending, we can refer to equation H1-1b. Although this equation is for combined bending and axial force, in the case of unsymmetrical bending without any axial force, we can omit the first term and we will be left with the second and the third term. In this equation, Mrx and Mry are the required design flexure strength about the x and y axes, and the Mcx and Mcy are the design flexure strength about the x and y axes. So, using this equation without the axial term, we can ensure that the combined moment about both the principal axes is less than the corresponding capacities in both the directions.